it's not too early. So it's not too early. So it is definitely no trouble to be here today. And I'm excited to present a bit on some of the work I've done as part of my PhD. In particular, this is work that I've done with, there we go, with a collaboration with Lawrence Livermore National Lab. So with Jonathan Dubois at the lab there. And then this is also work, so I'm a physics PhD student, but I'm advised by Nathan Kutz in the applied math department. And this work was also done with Steve Brunton and Ulrike Kaiser in mechanical engineering here at the UW. And so just a few different, funding things to thank, but yeah, so this was born out of this collaboration at Lawrence Livermore, and kind of one of the questions that Jonathan brought to us was a question about how to design accurate control schemes in kind of a setting where the given models are inadequate. So this is kind of a place where the motivating point was about coherent errors and kind of the underlying models describing kind of his superconducting qubit systems. But it kind of is just a general framework for a lot of the work that we did in what's essentially become this NSF AI Institute in Dynamic Systems here at the UW. And so the two pieces, so I was introduced on one half of it, but we're also going to talk about this learning component. So this notion of data-driven discovery of models for quantum control dynamics. So we're going to talk about this in addition to some of the planning work that we talked about with model predictive control. And so to break it out in this way, I just kind of want to give a sort of bird's eye view of why I want to use these two components. And so to do this, I'm going to steal this survey article on model-based reinforcement learning, where they kind of adapted a picture from the Sutton and Bartow RL book. And so this is kind of an RL, maybe focused overview of what control looks like, but I think it's useful because it kind of has these learning components which focus on adapting control strategies when maybe you don't have a perfect model. So we've got these components here. We've got the model, we've got this planning stage like we talked about. We also have kind of standard RL components, either a global policy or value function that tell you how to kind of make decisions in the full state space of the system. And so I just kind of want to draw a few plots onto this that indicate kind of what traditional control or other kind of control strategies look like. So we have traditional control here, which is you've got a very good model of your system. And so what you can do is you can design some sort of open loop control law, a plan, which gives you actions that you can synthesize onto the system in order to realize some desired outcome. And so that's perfect when your model is very solid. And of course, you can introduce feedback and things like this with the data in order to maybe close this loop. But that's the core idea, is that if you have a very good model, life's good. All you have to do is make a plan and follow those actions. And kind of the opposite extreme, model-free reinforcement learning, which has been applied, widely, but even in the quantum setting, it has this notion of these global policy or value functions. And so you make no kind of assertions about the structure of the model of a system, and instead you try to just evaluate the quality of the state space in order to determine the actions. And these are basically something which are informed by lots and lots of data. So it takes a ton of data in order to constrain these, but once you have them, they're incredibly valuable because they indicate basically every sort of action in the entirety of the state space. And so this is where kind of your notion that we're very familiar with in the quantum community, this like curse of dimensionality due to an exponential state space. This is kind of, that term was first introduced in this setting where you're talking about the state space that you started to deal with for these kinds of systems. In this talk, what I want to do is kind of traverse our chart in this particular way. And so that's going to kind of be the guiding picture to have in mind for the work that I've done as part of my PhD here in this collaboration with Lawrence Livermore. And in particular, we're going to talk about two parts. So this first part is going to be my work on what's known as the bilinear dynamic mode decomposition. But essentially, this is going to be a way to do kind of model discovery for the particular structure of quantum control dynamics. And then in the second part, we're going to talk about a planning stage, which is this work on model predictive control. And so these two components, as indicated by this chart, really do integrate together in kind of a useful way, but also kind of, we're just going to introduce them separately and then kind of hint at the ways in which that integration makes sense. Okay, and of course, I guess it's also useful to sort of emphasize there are other ways in which this chart can connect up to inform kind of how you might do some sort of component-based integration in order to do better control. So here, this was the kind of AlphaZero strategy made famous by the Google team in their algorithms, which performed better on things like Go and chess, and have even done things like playing StarCraft, where you have maybe a fixed model for the rules of your game. And then you sort of integrate your planning, which is in a discrete action space, and it's some sort of tree search with these global policy or value functions, which basically inform how that tree search occurs. And so this integration is just another kind of picture to have in mind that this is kind of a lot to explore about how you might make these choices in order to improve your control of your system. Okay, so I just want to give a few examples of the kinds of modeling challenges that I want to use to motivate this work, just so that we all kind of have, some picture in mind of, okay, let's apply this or that. But what I want to do is just look at kind of Hamiltonian systems to describe the control dynamics. So I've got some exogenous actuation, U, and some of the challenges I might have is I might have some sort of coherent error in the characterization of my system. And so that leads to some unknown Hamiltonian term. I might have nonlinear control distortions where I've characterized the effect of my control, but maybe I've done that at some temperature, but then I cool the system down. And so I end up with this kind of transfer function, which affects the actual control inputs of my system. It's also the case that you might have noise, which can either lead to necessarily describing your system with some sort of open quantum Liouville equation in the Markovian case, but also maybe this is still not appropriate and you have to switch to some non-Markovian description. There's also leakage, where your system is basically interacting with higher levels of the system that maybe you didn't intend to compute with. And the scaling challenges associated with the fact that as you interact with maybe some subsystem and are trying to control that, as you scale things up, there might be some unintended couplings that you did not expect to have enacted on your system. Okay, so those will just kind of come in and out as we need to kind of provide motivating examples and applications to the sort of methods-driven talk that we're going to hit today. All right, so this part is the learning section. And to just kind of outline what I'm going to do, I want to introduce sort of a notion of quantum system identification. And I'm going to do that through what's known as the dynamic mode decomposition. And then I'm going to basically adapt that to the quantum control setting, which is going to lead us to this bilinear dynamic mode decomposition. And then I'm just going to briefly hit some of the extensions that, the kind of perspective that we're going to talk about here will provide. Okay, so for the purpose of this section, I think it's key to kind of step back and say, well, what are we doing? We're doing model discovery. And so in this setting, the model is unknown and must be learned. And we're basically working directly with data from simulation or experiment. So what I mean here is that, you might have some known Hamiltonian describing your system, your control effects. We're going to kind of ignore that for now. But of course, all of these methods could be applied to a discrepancy model for the system, sort of the error term, just as well as they could be applied to kind of the full system. So that's not really going to be any loss for us. It's just going to kind of be something to have in mind that you would have basically that extra information that you would rely on. So the first piece, in order to introduce the dynamic mode decomposition, I want to talk a little bit about a component of model reduction. And so in order to do this, I'm going to introduce the Olivetti faces data set just to give us some grounding here. So this is just a bunch of pictures of faces cropped in on kind of to highlight shared features between this set of IBM engineers at the Olivetti labs in the 90s. So you've got all these goofy pictures of different folks. It's kind of a classic ML data set. And an analysis to sort of define what we mean by shared features of all these faces is performed basically by just doing a principal component analysis. So what you're going to do is you're going to form a matrix basically of all these faces, put them in columns into this X, and then you're just going to take the singular value decomposition. And so what I want to emphasize is just the motivation here is just find some sort of straightforward low rank description. And so that's where the SVD comes in, and these basically pink modes here, these eigenvalues, are going to describe basically the most variance in the data set. So this captures a lot of the information of the system. And you can even look at the column space eigenmodes of that data set. And what you see with these kind of Lynchian nightmare faces is that you've got 3 modes which capture a lot of the core features of your data set and provide a reasonable basis in which to describe that system. Okay, now, in order to build to the dynamic mode decomposition, what I want to do is emphasize that I'm looking for reduced order models for dynamics. And in order to introduce the idea of dynamics, let's just ground this with a specific example. So I'm going to take this transverse field Ising Hamiltonian in order to kind of tie my work to examples of other kinds of basically basis learning for low-rank descriptions of quantum dynamics. So this Carleo and Troyer paper, but also here this quantum system compression paper as well. So I'm going to take this with an on-site energy H and some coupling between nearest neighbors. And what I want to do is just look at some data because we're doing data-driven methods. I'm going to simulate the quench dynamics starting with H equals 4 as ground state and quenching that parameter to 2. And I'm going to do this for, I think, a 10 qubit system. So just a cartoon here, but it's about significantly higher than what would fit in this picture. Okay, so I just want to emphasize that the core component of what we're going to try to pursue is based on this notion of a snapshot method. And so the idea here is that, again, just like the Olivetti faces, we're going to form a snapshot matrix. And I'm just going to plop in from time 0 to time 2, 200 snapshots. So let's say I've taken 200 measurements of the system. I've got psi 1, psi 2. I could jumble these however I want. They're just a collection of pictures, just like my faces. So I could just as well have psi 17, psi 20, psi 200, and then psi 2. The point is that, again, I can chase the singular value decomposition in order to describe a straightforward dimensionality reduction of my system. So that's what I've done here. And you might say, great, you found a perfect basis to describe this system. Note this truncates at 200 because I had 200 snapshots. So I'm rank limited by the data that I've taken. But yeah, I've basically captured all of the information of that time 0 to time 2 system in these first 16 modes. Of course, I could go even further and say, well, is that a good basis to describe the dynamics of my system, both in that first 0 to 2 time and in the future? And so in order to do that, I can just expand the quench dynamics, not just from 0 to 2, but maybe let's go predictive and go out to 4. So I can inspect the trajectory. We'll just look at that in these polar plots here. So let's look at the first 8 modes, the coefficient dynamics. So of course, what you see is you've got your standard static mode, and then you have modes which look periodic and some which do not. So you start to look at this and you say, well, I didn't really capture maybe a basis that was totally appropriate by just looking at kind of the first kind of naive low rank description of the system I could consider. And the key point here is that I didn't make any temporal assumptions about the system. So the notion we'd like to retain, and this is what's going to drive the idea of our system identification through the dynamic mode decomposition, is can we retain the known underlying Hamiltonian structure? That's exactly what you do in the dynamic mode decomposition. One way to think about what this algorithm is it's a way to expand our quench dynamics in a basis which inserts some sort of structure for what the time dynamics should be. And it does this entirely in the same data-driven way that we've been pursuing. And so this is kind of the idea. We want trajectories which are kind of meaningful in a very predictive sense for the kinds of dynamics that we've just asserted we have, which is this kind of Hamiltonian or operator picture. So that's the motivation for this algorithm. In general, what DMD is it's this notion of finding a generator, an operator like a Hamiltonian, that describes the dynamics of a collection of observables. So this originally was an idea in the fluid dynamics community, but because it's based on kind of an operator theoretic picture where you have measurements of the fluid system or snapshots of the system, as opposed to any sort of inherent phase space description, it actually is a lot broader. And it connects back to sort of in classical dynamical systems, the notion of dynamics through the Koopman-von Neumann theory. And so this is kind of reframing classical dynamics with the same mathematical framework of quantum mechanics, where you've got operators acting on some Hilbert space of observables. So that's kind of just the theoretical connection idea here. But the actual statement is relatively straightforward and what has led to kind of like a broad application area for these methods. So what you do is you collect data. It might be snapshots of some flow here. It might be some sort of set of observables. But what you do is you then assemble snapshot matrices. And here what's important is instead of just taking some jumble of faces or pictures, we actually make sure that we structure our system so that we have offset matrices by one time step. Okay, so we have this X and this X prime. And then what we do is we just connect those through some operator. So a relatively straightforward idea, connect these two with an operator, which describes basically the kinds of dynamics we're expecting. And then through the DMD algorithm, here I've represented it with this Frobenius norm here, but the idea is you construct this operator A directly from the data of your system or the simulation of your system or the synthesis of the two. I want to highlight the fact that, of course, we don't want to, in the case of fluid flows or something where you might have millions or billions of terms to describe your state, you don't want to construct this full A, but you just want to highlight kind of the components that you care about, that low rank description. So the algorithm actually avoids constructing the full A. It is optimization based. And so what's nice about that is it accommodates very naturally things like compressed sensing, which is important for kind of the quantum mechanical setting, but also for the fluid setting or anything like that. And it very naturally accommodates physical constraints. So it fits very well into this notion of physics-informed machine learning, which would be the way to kind of communicate that now. And so it does that through what's known as Krusty's problems. And so there's a lot of kind of recent research that kind of has reviewed and sort of extended those ideas. And again, because it's so widely applied, there are a lot of extensions and adaptations of this method. So let's look at how we did. So this is that time 0 to time 4 prediction that we were just talking about for our transverse field Ising model. And we see that our basis is now much more appropriate to describe the system. We've got some of the structure that we intended to keep in those first 8 modes instead of what we had looked at before. Okay, so that was a lot about what dynamic mode decomposition is, but I'm interested in control and in particular learning the control dynamics directly from data. And so in order to do that, I have to basically adapt DMD to something like DMD with control. So what I'm going to do is I'm going to record the state and the control. I'm going to basically treat this control like another state parameter. I'm going to assemble these snapshot matrices, and then I'm just going to compute a regression like so. This emerged actually out of the epidemiology community because the notion was you can't really ever turn off this control in certain settings. So you might not have the ability to just stop vaccinating or something like this. And so you had to kind of address and discover the model of your system in a setting where this was always going to be part of the dynamics. What we need to do is we need to modify DMDC for the setting of quantum control. And of course, quantum control dynamics are bilinear. In the Hamiltonian setting, it looks something like this. We've got a drift and control Hamiltonians paired to each of your control inputs. So in terms of these snapshot matrices that I've been talking about, what we want is something like this, where you have this nonlinear data term here. So we can walk through that and just say, okay, we want to assemble the snapshot matrices as before. We want to multiply, we want to compute this nonlinear term with this Cauchy-Rao product, which is just a tensor product respecting the time dimension. And then we're going to compute the regression. So straightforward, but we retain all of the nice stuff that we talked about before, the notion of dimensionality reduction, the notion of constraints and physics-informed learning, all of that coming from basically basing this method on the dynamic mode decomposition. One piece that you might need when pursuing this method is something which comes kind of from what I had talked about before, this Koopman operator community for the classical dynamics, which is extending some of the data elements because basically we can always lift our data into a higher space. And so we can do that with the control by basically taking higher order powers of our control input. And the reason we might do this is, of course, we're not going to lose anything because higher order integrators are basically going to remain control affine in the dynamics. That is, we put u and u squared and u cubed in there, that's totally fine. Integrators basically incorporate those terms to higher order in the discrete expansion of the system. It's also necessary in order to discover nonlinear control distortions, one of those modeling errors we talked about. And it's often the case that effective Hamiltonians basically with dynamics which you don't intend to keep in the interacting space that you're interested in produce lifted controls. So this would be something like taking a Schrieffer-Wolff transformation and finding that basically you produced higher order control powers or something as you reduce the dynamics into some sort of subspace. So let's ground this in just kind of some cartoon examples. So instead of kind of keeping that transverse field Ising model, let's go even simpler and just really focus on what we talked about the bilinear dynamic mode decomposition doing, which is separating drift terms from control terms and identifying them simultaneously from data. So the data I'm going to use is I'm going to actuate my system on basically the x-axis here, and I'm just going to take some snapshots of my state, and just to kind of highlight what I was talking about with the lifting, we'll just lift to fourth order in the control. But of course, I could have not bothered with this, but the point is we don't lose anything, so we'll just do that. And so here's one of those modeling challenges I talked about, where we have basically a drift term that's unknown, a control term that's unknown. It might be that you're actually trying to capture some sort of discrepancy on the system, but for here, let's just take them both as unknown. And so what we want to do is we want to take snapshots of the system represented by these open circles for some control pulse applied to the system. So here I've just taken something which is basically a 2π pulse. I've got some drift term here, you can see, affecting the x component of the system. And I've got some spinning around going on y and z. And so after I've taken these snapshots, what I can do is I can construct my bilinear DMD model like we had talked about. And then I can basically reapply the control amplitude as an exogenous input and just kind of integrate that model forward. And what we see is basically we're able to reconstruct using only the initial condition and control input. And that's exactly what we wanted. We wanted something which basically separated the impact of control from the drift dynamics in such a way where we basically had access to using that model to control the system. What that means is that if we were to take this physical simulation here and say we wanted to produce with a different control input, something which looks like this system here, we could use that same bilinear DMD model trained on that kind of Gaussian pulse that we just saw previously. And we could say we should expect to see something like this. And that's exactly right. We are able to reproduce just from the initial condition in the application of that control input, something which captures the core features of that data. Now, of course, there's this decrease here, which would is pretty natural and just kind of the naive application of dynamic mode decomposition. This is just due to the fact that basically the eigenvalues have pushed in a bit on the unit circle. This is something which benefits from additional constraints on the system and is relatively straightforward to implement through the notion of these Procrustes optimization problems that I've talked about before, and which is work one of our collaborator, or one of the people works with our group has kind of pushed along recently to great success. So okay, another example of how this might impact our ability to identify systems is through these nonlinear control distortions. So what I've got here is, remember, this transfer function acting on U. So I've characterized my system expecting it to behave in a certain way with U, but the actual impact of my controls is modified by this function theta. So here would be my, let's say I've got some wiggled envelope here of my pulse on my just straightforward block sphere qubit. And what I'm doing is I'm trying to produce some sort of behavior. And this is what my expected behavior looks like for my system. But if it's the case that I've added this nonlinear control transfer, so I've just added a really straightforward tiny term here, and I've modified my control input slightly. But you see that it completely muddies up what I had expected my dynamics to do. So the question is, what can I do? Well, I could train through this notion of snapshots again by collecting basically my gray control U and snapshots of the resulting dynamics for these two, let's say these two training pulses, just kind of arbitrary pulses here, just to kind of give a sense of it doesn't really depend as long as the input is rich. You have just gray lines here that you're going to take data and assemble the snapshot matrices and these outputs here. And then after you build that bilinear DMD model, what you can do is you can test that by just feeding in these gray control inputs. And what BiDMD does is, because it's completely data driven, it has no knowledge of what the underlying dynamics should be. It's just trying to capture kind of what fits the data the best. It learns this nonlinear transfer function. And what's important about this is I didn't really change the structure of how I was learning my model. So what I want to emphasize is in the first picture, example 1, I had no knowledge of basically what my drifter control dynamics were. And in this picture, I have a transfer function affecting the system, but I didn't have to change by DMD to account for kind of these two different settings. It just naturally, because it's based on data and is kind of agnostic to the underlying model, it's able to capture whatever your kind of issues are in this framework. And just kind of two small points I want to hit is this notion, it's all built on this notion of basically we're working directly with data. So remember, we kind of played with this just a bit by lifting the control, which was something that is kind of connected to ideas in this community, but it goes a little bit broader than that. We can work with augmented states like taking past measurements and including those as part of the current state. So that means that basically instead of just my snapshot being X1, it might be a time history which goes back to XS, or excuse me, it might be XS goes back to X1. So basically you have some time history, and that might include, however many measurements you want to retain. And so what you've captured here is basically some sort of trailing history, which would give you a chance to capture kind of perhaps non-Markovian effects in the system. And this lifting is possible because you're just working with data. And so you're just trying to capture some model for your system based on the data you've collected. And so you just kind of offset those like you'd expect for these time delay embeddings is what they're called. And this is connections to the eigensystem realization algorithm, which is basically a system identification approach, which has previously been applied to quantum Hamiltonian identification. So just kind of a nice connection back to previous methods with a straightforward modification of what our snapshot is. You can do this as well by considering drives retained within one stroboscopic period of the system. So if you just take this snapshot here as measurements entirely within one period of the drive of the system, and then this one maybe is within the next period, and so on and so forth, and you offset basically by one period your next snapshots, this has connections to flow K theory and allows you to handle kind of a complicated stroboscopic driving or measurement strategy. And so that's just kind of another connection, which is entirely just immediate once you have adapted what your snapshot actually ends up being. So that's just kind of a quick note about what this kind of data-driven approach really buys you, which is a lot of flexibility about what the notion of state is. So in this section of the talk, kind of what I want to highlight is there were many ways for modeling to go wrong. Isolating each of these errors could be difficult. And what bilinear DMD does is it incorporated all those unknown dynamics in an interpretable way. Okay. So in this second part of the talk, what I want to do is I want to highlight a little bit about planning. And so in particular,
can I ask a question?
Absolutely, yeah.
Yeah, you said, okay, so if I understand correctly, what we get from this is the ability to predict the dynamics using some reduced model. But the model is not in the same, let's say, language as physicists would do, right? So the transfer function for the controls doesn't look like a transfer function for the controls in A, right? In the A matrix. Not directly, at least. You could maybe extract it somehow, but it's not a trivial endeavor.
Yeah, so it is a bit of a different perspective. And so, yeah, so there are ways that these kind of system identification methods connect to kind of more traditional transfer function pictures. But yeah, this is just a different perspective where you're kind of looking at a straightforward identification of a model in this kind of data space. And so, yeah, so it's not necessarily a natural connection, but if what you're interested in is designing algorithms to control your system, this is kind of one approach which can integrate well in what we showed on kind of the first chart there, can integrate well with kind of that modeling stage and adapt to kind of maybe other components of how you would build kind of open loop controllers for your system.
Yeah, no, I'm not doubting the value of the effort. I'm just trying to clarify it for myself because I'm coming from a very physics-based perspective. So there, when we have a transfer function and we learn it, at the end of the day, we have a transfer function. And here we have something with a transfer function, and we end up with a very effective control tool, but no direct knowledge of, let's say, Hamiltonians and transfer functions and whatever other phenomena may occur.
Right. Oh yeah. So in this case, yeah. So you maybe are not particularly interested exactly. So there's kind of an agnostic nature to like the perhaps underlying model of the system as opposed to the sort of effective model, which is actually being basically produced by the actions you're taking. So yeah. So this is kind of like producing effective models, not necessarily always some true Hamiltonian describing the system, whatever that might mean for very important interpretation questions of like, okay, I really know what part is Hamiltonian, what part is error, and how all these effects integrate. So that's much more subtle than what kind of we're talking about here. So kind of that's the trade-off, I guess, and that's a good point. Is you're trading off sort of this effective modeling angle, and you're kind of sacrificing, basically distinguishing maybe these effects by integrating them all into one kind of effective modeling framework. Yes.
Thank you very much.
Yeah, absolutely. And that's a great point to kind of emphasize for how a lot of these approaches end up working in the other communities as well, as you kind of are making a trade of insight maybe into the physical nature of the system much more for these effective models, whether it's physics or for quantum or fluids or anything like this. Great. And so in the second part of the talk, what we're going to do is we're going to kind of shift gears and talk a little bit about model predictive control. And so in the first part, I'm going to just introduce what model predictive control is. Just checking to see where we're at on time. Okay, and so the key kind of perspective I want to invoke for what model predictive control is this notion of planning, acting, and then repeating. And so the idea here is that you might make a plan. Basically, let's say you're trying to catch a ball that's been hit by somebody in like a baseball game or something. And so you could make a plan for the instant that that ball comes off the bat, and you could try to run to exactly the spot that you think that ball is going to go. Based on your knowledge of the physics of the system, you could have the robot or the player run to exactly the right point, lift their arm in exactly the right way, and catch that ball. And of course, that might work really well if your model is perfect and you do everything right. But based on basically interactions with the environment or modeling errors, it might be the case that that's not a good approach. And that what you want to do is basically reevaluate, look at where the ball has ended up, and make new plans basically after you've acted in that environment in order to adapt your strategy. And so in particular, let's look at more concretely what that looks like by this cartoon where I'm going to have a state up top, a control on the bottom. And what I'm going to do in this planning stage, followed by the acting stage. In the planning stage, I'm going to solve a model-based optimal control problem over a fixed horizon. So in this case, I'm going to do some sort of direct optimization where basically I return an optimal solution for the state and the control constrained by the dynamics of my system. And then in the acting stage, I'm just going to apply one control step and acquire data. And it might be the case that basically my data acquired is offset from basically what I had expected the system to do. So acquiring data in the quantum setting means running an ensemble of experiments and applying some sort of state tomography. And so I'll make some comments on that in a bit. But the notion here is that after you've acquired that data, you can make a planning stage from that new point. So you can begin the optimization from this new state. And this gives you this certain degree of disturbance rejection. And so what you can do is then apply, like before, again, one step of the control sequence. And in this way, you can kind of repeat each past control sequence and append the new action. So you can kind of take this forward-looking approach to synthesizing this control pulse, okay? And so what this does is at each stage, it gives you access to basically the fact that your model predictions are using these model-based optimizations. And as a result, they allow for the control of multi-input, multi-output systems under state and input constraints. So you get kind of very powerful control design algorithms accessible to you at each of these kind of horizon-based optimizations. Okay, so we've got this static reference here as basically what we were trying to realize, but I just want to emphasize that within the model predictive control framework in general, you could imagine tracking a static reference, a time-dependent reference, or some sort of geometric path where it's not about time, but about how close you are to some particular trajectory or geometry in space of the state. But the point here was that there are a number of advantages we tried to highlight, and that was this natural disturbance rejection due to the measurement feedback, the fact that you were able to handle complex multi-input, multi-output systems under state and input constraints, and the fact that, well, we didn't really hit this, but I want to emphasize it now. Model predictive control is very flexible and adaptive. So it's not necessarily a new control strategy so much as it is a framework for integrating and utilizing existing control strategies. And so that means that you can really adapt MPC to a lot of different settings. And so that's very important. But yeah, another piece that's maybe key to emphasize is the fact that model predictive control requires much less data than something like a reinforcement learning approach. And that's because you're basically making all of your measurements along the trajectories that the model has you following. And so instead of just exploring kind of the entirety of state space, you stay restricted to basically the trajectories and states that you actually arrive at through the planning based on your model. Okay, so again, just back to this notion of bilinear dynamics, I'm going to have to do some sort of nonlinear model predictive control for quantum control. And so in order to do that, we had talked about how we were using basically this direct approach where I have state and input constraints on my system. And so that means that this nonlinear model predictive control, or excuse me, state and input optimizations for my system under a constraint of the dynamics of the system. And so what that means is that I'm going to solve this approach through something known as sequential quadratic programming. And you know, if I decided to solve this differently, there are a number of other approaches that I might pursue. But this is going to be how we're going to do it for this section here. Okay, so just to kind of hit then an example which motivates some of this work, I want to talk about this modeling challenge here where we have leakage to non-qubit states. So what I mean is I'm targeting my basically two-level system here, and I'd like to have isolated basically all these higher levels away from the system. But due to engineering constraints, what happens is I might have a weakly-anharmonic oscillator where these level spacings are just sort of subtly offset basically for my 0-1 transition. And so it might be the case that while I'm driving at this resonance here, I have an envelope on my drive pulse, which basically produces some non-zero spectral overlap with the other transitions that I've tried to ignore. And that leads to excitations and leakage out of my qubit subspace. So we can look at exactly that through a picture here. So if I were to apply a pi pulse to a qubit system, which had basically this weak anharmonicity that we talked about, that basically there are these higher levels present, but I'm not modeling them here, then what or not thinking about them here, what I've got is basically an application of a pi pulse, which should basically take my 0 state and rotate it up to a 1 state. And what we see is that basically as I try to do that, my population falls, but I don't actually excite the 1 state as I intended. And that's due to the fact that I had this leakage here out into the higher levels. And so what we talked about and what's evoked by the analytic drag scheme is that basically you can do some sort of derivative reduction of this leakage term by basically correcting through pulse coordination for that spectral overlap. And so what we have here is we apply this pi pulse, we cancel out basically that leakage term, and you see that we can suppress that leakage and excite the or transfer the population like we intended. Okay, so that's an analytic scheme. And what I want to do is basically highlight kind of some examples for model predictive control in this setting. So first and foremost, I just want to emphasize this is the same picture we just saw on the previous slide. And so if I provide the correct kind of good model for model predictive control to utilize, then you can see that basically under the kind of input constraints that I've provided in order to mirror something similar to the pulse up here, we produce a scheme which looks very similar to the analytic drag scheme that we saw before. So again, I've got some state measurements here during which I'm doing my planning. And the point is that basically, unsurprising because it's a numerical optimization as opposed to an analytic scheme, I'm able to synthesize something which looks similar to drag, suppresses this leakage, but does an even better job. But of course, this was under the case of a good model. This is kind of expected, obvious behavior. And what I want to highlight in this example is the notion that model predictive control is robust. And what I mean by that is if I use a bad model, that is, I forget entirely about the anharmonicity of my system, what I can do is I can make a plan which basically knows how to coordinate these two pulses just through the notion that I've taken some feedback and I have basically made new plans during the evaluation of where I've actually ended up. So basically, as I move forward, I find myself in certain states, and then I make my plan based on the actual position that I'm in. And due to that fact, I inherit this notion of disturbance rejection that we talked about, and I'm actually able to, as things settle out through a slightly longer settling time, I'm able to realize the kind of transfer that I intended. I can even try to not measure or basically disregard any information about that higher level by just kind of pretending I have measurements only in the 2-qubit space. And if I do that, I still see that even in this kind of pretty miserable case of data that I'm acquiring about my system, I have some sort of pulse coordination just through this notion of disturbance rejection and modifying my plans over time. And so there's always this coordination effect at play, which allows us to realize something which improves upon kind of our naive application of just a pi pulse to the system. Okay, so the takeaways that I want to emphasize from this and what we're trying to sort of push forward is this notion that model predictive control strategies are robust when model discrepancies are present, so that you don't need a perfect model if you're using something like model predictive control. The other takeaway was that you could enforce state and input constraints in these finite horizon optimizations. So it's got access to these much more powerful algorithms for doing your planning. And something we highlighted before, but I want to just emphasize again, is these model-based MPC have lower data costs compared to model-free RL. And that's because you basically are doing all your measurements along the trajectories basically planned by the model. And so you kind of have, in this exploration-exploitation trade-off, you have a much stronger bias on exploitation of the existing model, as opposed to very exploration-heavy model-free RL. Okay, so we have a number of other examples in the paper, which include things like crosstalk and kind of just other explorations of the kind of like parameters that you have access to in model predictive control, but hopefully that evokes the right idea of this robustness that I want to highlight. So what we had done in this talk is we kind of hit this modeling stage and this planning stage. I just want to emphasize that a lot of the work I'm interested in is this notion of targeting better integration. So we saw that basically there are all these really nice results like AlphaZero or something, which look at basically how to move across this chart and integrate these components in a way which gives you very effective controls in very challenging environments. And so that's kind of what had motivated this project during my PhD, was this notion of looking at these different components and also kind of exploring the ways they integrate. So that's something that we didn't really talk about in this talk, but you could imagine basically doing some sort of model construction through DMD, making planning through model predictive control. And then as you act on your system and acquire data, doing some online update or something of this by DMD model, making new short-term plans, which incorporate an even better model, and basically inheriting robustness here and adapting your model here in order to realize maybe a better control strategy or something like this. So this is this notion of integration. Of course, a lot of this talk was on small systems in the examples, but the key is that you want to scale these methods up, because kind of some of the NISQ era benefits to these approaches is improvements to pulse level optimization of basically quantum gates, but also common algorithm subroutines at scale. So basically looking at ways to pursue these kinds of data-driven approaches in larger systems, which is going to require a handful of adjustments. And then, of course, these are tailored to the specific quantum hardware of the system due to the fact that they are entirely working with data about those systems. So this is the summary slide, which has the two papers that I talked about in this chat here today. I've got a website here where you can look at and find some of my other work. And both of these projects have code, which is up on my GitHub. So yeah, so I've at this point, hopefully time for a few questions. But yeah, thanks for your time, and look forward to hearing from everyone now. So thank you.
All right, thank you so much for the talk. And I'll start. I have questions, so I'll start first. I do that because I'm the host, but yeah, we will have time for more questions. Yeah, so model predictive control, even though it had been around for quite a bit of time, it only picked up maybe in the last couple of decades because computational power came on track with being able to get that feedback, calculate the controls for the new step and then do that. How does this work with quantum systems? Like when you integrate it with an actual experiment, do you expect any issues with that, like to get the whole feedback cycle working while deriving the controls?
So you're in a setting where you're limited not so much by kind of these sort of challenging model predictive control calculations, because yeah, you're basically running an ensemble of experiments and then just running a tomography experiment to get these state measurements. And so you're kind of just limited by the amount of time that it would take to produce a reasonable tomographic estimate for the state of your system, or something, some sort of sparse estimate for that system, depending on what you're kind of doing. So that's kind of the limiting factor, is basically sensor measurements. And that's something that there's a lot of literature on in the model predictive control community, is basically, how much do you rely on my underlying model for my system, basically simulating that forward through the algorithm before I receive my next measurement update. And so you don't necessarily have the same constraints where you have to put like your model predictive control algorithm on a robot, and basically you're struggling with maybe like how long it takes to solve that optimization problem, because this can all kind of happen offline on kind of a large computer, as opposed to being embedded in the system, which is one nice feature. But yeah, you're entirely basically limited by how frequently you want to make those measurement updates, which, because it's a quantum system, it's basically just how long you would take to run this ensemble of experiments. But the literature, nicely for model predictive control, kind of has a lot about reliance on basically simulation, or basically how long these gaps can be, depending on the quality of the model. And something we're looking at in the future is basically how to kind of think about and improve that kind of challenge. So I think there's a little bit in the paper about exactly that question of like reliance on how quick these data updates occur. And then that's something that we're actually, actively interested in discussing further. So yeah, I think that's a really good question. But I don't think it has like a lot of the same challenges. They're a little bit different than like an embedded algorithm on a robot or something like this.
Okay, so then let's see what other questions do we have. Fila, you want to go next? Oh, okay, yeah.
Sure, thanks. Thank you for the talk, first of all. I thought it was really nice. I enjoyed the kind of graphics you were showing. I have one question on the talk and one follow-up to Anurag's question. So the first one was, you showed kind of bad model, ugly model, nice model, and where you get in the end. And I'm wondering, in order to get to that point that you show in the end, how much has to happen in between? Like, how many iterations do you need in order to get to that kind of point? And how much does it change for good, bad, and ugly model?
So all of these use the same number of measurements. So again, yeah, so kind of like the naive angle on what we're kind of trying to demonstrate here is that we're just walking this forward, kind of like treating the quantum system as if you can make no retroactive corrections, but that you're just going to kind of force the system to push forward as it goes along. And so what that allows you to do is it allows you to force basically all changes that the system must make to basically synthesize something better to occur forward in time. So all of these examples take the same amount of measurements of the system, and basically all of the correction occurs in how the model looks at basically where the quantum state is now and updates the plan according to that new state. And so that's where all of the kind of work gets done, is forward. So there's no change in what each of these utilizes for the system. It's just a change in, it's just kind of a demonstration of it could do the same thing with different models.
In that case, okay, I slightly misunderstood a part there. In that case, I guess I would change my question to, how long do you kind of have to tweak your MPC algorithm for in order to get to such good results? Can you just download the GitHub, apply it to a model, and then it works? I mean, that would be incredible.
Yes. Yeah, in some sense, that's exactly right. So I mean, you could download the GitHub. You could try to find, all of the same stuff in MATLAB, something like this, and you could just start applying it. And the reason that it works so nicely for these settings is because basically, you're sort of relying a lot more on the measurement feedback and not on kind of a very long prediction horizon. So that was one of the things, remember when we saw about DMD, is we could build this model, and maybe we saw that, you had these predictions which sort of decayed over time. But one of the things that you're often doing in kind of maybe like a fluids community or something is you build this model from data. You know that it's only going to work for a short time window, and then you toss it out. And because it's so cheap to build again, you just reconstruct a new model for your kind of, next sort of set of points. And so it's this notion that basically these short time windows, you can do pretty well predicting. It's kind of doing the full time window where your errors start to accumulate and make it tough. And so if you can kind of eliminate the emergence of those errors by kind of always checking on what's actually going on with your system, you gain a lot. And so that's what you buy with this kind of framework.
Okay. All right. Thank you. Yeah, it's very nice to look at. I forgot my other question, so I'll just pass it.
Okay. So then Shai goes next.
Yeah.
Okay, so this is really interesting because you're thinking about exactly the same type of problems that I've been thinking about for a decade, but you're coming from a very different direction, which is cool. So one thing that bothers me is that I can try and phrase kind of the most comprehensive model I can for a qubit. So it'll contain dozens and dozens of parameters. The control function, the Hamiltonian itself, anharmonicities that don't behave the way they should, coupling to other components in the chip, etc., etc., etc. You end up with this really beefy, robust model with Markovian noise, non-Markovian noise, a million things. Okay. Now, this model is probably an overkill in many respects. And one thing that I have a feeling that the approach that you're detailing does very well is give us like a Taylor series of models, in the sense of, the most important effect, the secondary, the third, because you have your you have the eigenfaces, right? You have the series of eigenfaces for this, which is extremely valuable, because a big part of physics is knowing what's not important. And this is really good at it. The difficulty, and I'm going back to the question I asked kind of in the middle, is how do I translate the two languages to each other? So how do I translate, the standard physics modeling language to what is extracted from this approach?
Yeah, and I think perhaps the way I would do that, just kind of off cuff thinking, is I wouldn't throw out all the hard work you've already done. Maybe you focus on what you're very sure about, and you then try to use these data-driven methods to maybe capture, like you said, some of these other effects. And that's kind of what originally I was thinking of when I was pursuing this work, was this notion that maybe I have a really good sense of what the core Hamiltonian should be, and maybe I have some distribution around that. And rather than try to like perfectly characterize what that kind of distribution might be for like that specific device that I've built, it was, well, how can I just sort of make sort of from the data I'm getting an effective model to kind of make those corrections. So as far as actually going back and sort of trying to unravel what each of these effects are, that's kind of maybe not really what I wanted to do with this work. And so I think it's a very, yeah, it's a very different question, because I think, you know, what I was trying to avoid is basically I found all of that modeling intimidating, and I was like, wow, that's very impressive and hard. Is there just a way, you know, a lot of what our group does is just say, like, can I throw out a lot of that and just, like, if I just see something happening, construct those underlying models. And
Right.
so that was kind
the
of the
difference. Okay, so and that's a very legitimate approach. The issue that we're trying to contend with is the following. These are not natural systems that we're just trying to interact with, right? These are constructed systems. We're building it.
Right.
And they don't work as well as we hope, by definition, always, right?
Right.
So in order to understand exactly why not, I need to kind of phrase, so I need to somehow glean from the behavior of the system information that'll tell me what's kind of going wrong and why is it going wrong. What is it about the model, let's say, in the sense of what I understand, Hamiltonians, etc., that's limiting the performance. So and that's why I'm kind of insisting on a model from our definition of a model, right? The Hamiltonians, etc. Because if I say, well, this is exactly what's going on in the system, this is the model with a million parameters, I can start, you know, kind of playing what if, change parameters in the model, see if the performance can improve as a result, and then figure out what do I need to change in the next iteration of the hardware that I'm building. But maybe the problem is too much crosstalk between the control lines. Maybe it's a million things. So I'm kind of trying to figure out, but your method kind of finds a really reduced model, which is super important and useful, but it's somehow in the wrong language. And I'd love to figure out a way of using this data that you know how to extract and translate it back. I don't necessarily expect for you to have an answer for me. This is more of a research question.
I think that's a very strong point, and it is something that probably, if I were to think about for a little bit longer, I mean, just due to the kind of range of settings in which these methods have been applied, I can't imagine, you know, there's not you know, reasonable situations in which you're going to find people in different communities who are asking that same question and have good answers. I think one thing that's nice is that
would you suggest I talk to figure out that?
I think I can follow up with you offline, and so great. I will try to see if I can, you know, provide a much more structured answer for this question, because I think it's a good one, and I think it would be really helpful to kind of make that more concrete. Yeah.
Okay. Thank you very much.
Absolutely.
Martino.
Yeah. Okay. Hi, Andy. Thank you for the very nice talk. So I was wondering, so with this, I'm thinking more about the dynamical model composition and that part of the talk. So do you think that you could do something like that could also be useful later on for the control by not having access to the full state value of some operator? Because I think that would help a lot in the practical implementation of something like that in an experiment, because doing the full quantum state tomography at each step could be a little bit complicated. So what do you think about that?
Yeah, so there's a few points to make about that question. So first, yes, I think that there's a lot of valuable work to do, basically, in adapting kind of that system model that you're identifying with kind of also the measurement model for the system. And that's kind of for an engineering minded person, that's going to look like having a state space model and a measurement model, and you're trying to kind of just identify with that extra step, which is very standard. You know, that's something which you're going to pursue. About basically kind of finding the right things to measure, that's kind of a very interesting and active area of work in kind of this type of community. I think that there's a few approaches that are worth taking, which basically all are gonna basically revolve around the notion of some sort of correct kind of sparse sensing. So maybe to give an example of where this connects back to kind of the classical fields that I come from is a notion of like, I'm trying to measure maybe ocean temperatures or something like this. And I need to drop buoys in the ocean and it's very expensive. And so I can't just put a temperature sensor at every spot in the ocean in order to reconstruct kind of these global temperature modes. But what I can do is I can find maybe meaningful metrics for where to drop these buoys in to get very effective approximations for what those kind of low rank modes are. And the kind of core concept underlying that is this notion that I didn't need kind of a full, huge description of all this complicated substructure, but I had these kind of global modes that I was trying to extract. So when your system is low rank, there should be a very reasonable kind of compressed sensing set of measurements you can make in order to extract those larger modes. And so that was kind of one thing I tried to point to at the start of the talk, which was, yeah, basically extracting kind of these compressive sensing measurements. And there's extensions in both the dynamic mode decomposition community with some sort of compressed sensing dynamic mode decomposition from a handful of years ago that I know somebody in our group had looked at. But this kind of approach more broadly, I think, would be the one way to go for this work. But yeah, like measurement and sort of measurement in this data-driven perspective is another kind of very meaningful, and there's a lot of work that could be done there. But at the end of the day, yes, I think that there's stuff that can be done. And yes, you do need kind of, you do need the data in order to pursue these methods. But yeah, if your errors require that knowledge, you'll have to figure out how to do it. Exactly. Yeah.
All right. Thank you.
Yeah.
Okay. Do we have any more questions? I don't see any raised hands. So, okay. Seems like no more questions. Then we thank Andy once again for this very engaging and fruitful discussion and talk. So yeah, thank you once again. And I guess I'll see you guys next week for the next Control Club session. But yeah, then bye for now.
All right. Thank you, everyone.
Bye. Thank you.
Bye-bye.